You've probably done this a million times, right? Stretched a rubber band, played with a spring, you pull it, it gets longer, you let go, and snap, it goes right back. It seems so simple, but believe it or not, there's a beautiful, predictable law of physics running the whole show. And in this explainer, we're going to dig into the science of stretching and squashing to find it. All right, so let's start with a really basic question. We all know if you hang a heavy weight on a spring, it's going to stretch more than a light one. But is it just random, or is there something else going on, like a secret code, a precise mathematical pattern hiding in plain sight? Well, that's the mystery we're going to solve. Okay, first things first, we need to get a key idea down. Basically, anytime you push or pull on something and it changes its shape, you stretch it, you squash it, you bend it, there's a sciencey word for that. Deformation. Super simple, right? But it's the foundation for everything we're about to talk about. But here's the thing, not all deformation is the same. You've got two main types. On one hand, you have elastic things. The perfect example is a spring. You stretch it out, let go, and boom, it snaps right back. But on the other hand, you have inelastic materials. Think about a lump of clay. You squash it, and it just stays squashed. That permanent change is the big difference, and it's exactly where we're so interested in springs. So the big question is, how do we actually describe what these special elastic things are doing? Well, that brings us to the star of the show, a super elegant but really powerful rule discovered way back in the 17th century. And here it is. It's called Hooke's law. All it really says is that the extension, which is just a fancy way of saying how much something stretches, is directly proportional to the force you put on it. I know, directly proportional sounds kind of like textbook jargon, but trust me, the idea behind it is super, super simple. In fact, this quote breaks it down perfectly. All directly proportional means is that there's a perfect, predictable connection. You put twice the force on it, you get exactly twice the stretch. You use 3 times the force, you get 3 times the stretch. It's a perfect one-to-one relationship. It's that reliable. Okay, so the theory sounds good, right? But talk is cheap. How can we actually see this for ourselves? Let's put this law to the test with a really classic experiment. And the setup is really, really simple. You just hang a spring and you measure how long it is. Then you start adding some identical weights, one at a time. Every time you add a weight, you measure the new length, and then you figure out the extension. Just how much longer it got from where it started. It's a really straightforward process. And what happens when you start writing down the results? Well, you immediately see this incredible pattern emerge. Just look at these numbers. The force doubles from 0.1 to 0.2 newtons, and guess what? The extension also exactly doubles from 5 to 10 millimeters. The real-world data is perfectly lining up with the theory. It's amazing. When you see it as a chart like this, it becomes so obvious it practically smacks you in the face. Look, as the force bar goes up, the extension bar goes up, in perfect lockstep with it. That beautiful, clean, step-by-step growth, that is the picture of a directly proportional relationship. So what's the big takeaway here? It's that the spring's behavior isn't some random thing. It's totally predictable. Because of Hooke's law, if you tell me the force, I can tell you the stretch. Simple as that. But here's a question for you. Does this perfect pattern just go on forever? Well, as it turns out, even the best rules have their limits, and Hooke's law is no different. There is a point, a breaking point, you could say, where all of that nice, predictable behavior we just saw completely falls apart. And that point has a name. It's called the elastic limit. If you just keep adding more and more force, if you pull that spring too far, you push it beyond this magical limit, and once you've crossed that line, it's not going to go back. It won't snap back to its original size. It's been permanently changed, or to use the science term again, permanently deformed. But why? Why does that happen? We've all done it, right? You get a slinky, you stretch it out just a little too far, and it's ruined forever. So what's actually going on deep inside the metal when that spring just gives up? To understand that, we have to zoom way, way in, down to the molecular level. See, a spring is just a bunch of molecules, all held together by these tiny little forces, almost like microscopic glue. When you stretch it just a little, you're just tugging those bonds apart, and they're happy to pull right back into place. But if you yank it too hard, you actually break those bonds. And once they're broken, they don't just magically reform. The damage is done, and the spring can never go back to the way it was. Okay, so let's do a quick recap of everything. What is Hooke's law? Well, it's this really cool rule that perfectly describes the predictable link between force and stretch. The main thing to remember is that the stretch is directly proportional to the force. But, and this is a big but, it only works up to a certain point. That's the elastic limit. Push past that, and you've changed the object for good. And that kind of leaves us with a cool final thought, doesn't it? We get so focused on how elegant and perfect these laws of physics are, but sometimes the most fascinating science happens right at the edge, right at the point where the law breaks. Because understanding why a rule has limits, well, that often teaches us more about how the world really works than the rule itself.